All right, I'm going to talk about some of the features on what's going to be on your radio. That's what's in this chapter, and we're going to go through them rather quickly. Begin with is microphone gain. Microphone gain does what it says. It controls an amplifier for the audio going into the radio from your microphone. If you're running AM or single sideband, your AM on your microphone gain on a radio is going to increase the amplitude of the amplifier, the power amp out. And over modulating by having too much audio out will cause flat topping. You'll exceed the linear range of the final transistors. If you're running FM and you overmodulate, run too much audio, it's too heavy, why then you will increase the bandwidth or the standard deviation, the deviation of your FM signal, how much bandwidth it is sharing your audio in. When you do that, you will be outside of the range of the receiver on the other end. It will distort the audio, and you will be crowding into space greater than the FCC permits. If you're running 15 kilohertz wide FM, you will probably be 20 or some number in between 15 and 20. And that will not only violate the rules, but it will cause you to be unintelligible. If your audio is too low, let's look at those two things. In AM, if you're too low, you're just going to be weak. If you're too low in FM, then your bandwidth is going to be so narrow. Again, it will be distorted. It will be hard to understand you. Either way, the trick is to find a nice soft spot in the middle. Generally speaking, there's a handy way about this. In figure 5.6, it shows a microphone audio volume or microphone gain knob. Generally speaking, the midway point is a pretty safe spot to set it. Okay, now I'm going to talk about a couple other buttons here, knobs here. One of them is called an RIT. You won't use this in FM, but you will when you get to HF operations a lot. You won't use it much in otherwise. RIT allows you to shift where you're listening when you tune, so that if you have multiple people you're talking to and one of the guys is just off a little bit, you don't change your whole frequency. You just change the receiver on him. When you transmit, you'd still be on the same frequency you're supposed to be on, in case you forget to turn it back after he's done talking. So it gives you a little bit of a fine-tune adjustment on the receive frequency. And AF controls are for turning the volume up and down. Very simple to understand. Audio frequency control. AF squelch. Squelch is a means of turning off the speaker until a certain level of signal is present. For weak signal, squelch is ineffective, but particularly in FM, squelch makes it possible to have a jet quiet radio until somebody talks. And that works out pretty darn convenient. Every radio you have you're going to get, every two-way radio is going to have a circuit for push to talk. Push to talk turns on a microphone circuit, but it also turns off the receiver portion of the radio and turns on the transmitter part. Generally speaking, push to talks nowadays are a completion circuit to ground in the wiring, so that the push to talk switch grounds out the input into the radio, and that engages the circuitry that controls the transmit receive switching, and the transmit power and transmit amplifier coming on. A type of push to talk which is automated in some radios is Vox, which is voice activated transmit. I don't know how they make transmit out of X, but trust me, it's right. Well, Vox circuits will automatically do the push to talk for you when you start talking at a sufficient level for whatever they're set for. Okay. Now, a Morse code is mentioned in here. It's not mandatory, but just so you know, Morse code is something you may want to one day get into. Read that parts of the book. It's good for you, but it won't really apply. It does, though, ask you about what an electronic keyer is. And understand that in Morse code, generally, the first 50 years was manual keying, and they had a device that we now refer to as a straight key. And later, they had a thing they referred to as a bug, which had like a flying contact, which would make the dots, but you still had to manually make the durations of the dashes. An electronic keyer is an electronic circuit that has basically two switches. One switch makes all dots, one switch makes all dashes. So you hook what's called a paddle to it. You hook that up to the radio, although some radios have them built in. And if you're sending Morse code, you can send dots and dashes by pushing one side or the other, which is basically making one switch or the other. All right. I'm going to jump down here to where it says peak envelope power. Peak envelope power is a measure of an AM signal's power. We can measure peak envelope power on an AM signal, and is principally how we're able to measure CW signals and FM signals. It's not effective it's not as effective in single sideband and AM for measuring power output, because the peak changes in AM transmissions. We measure peak peak envelope power. We're talking, though, about the peak power of the envelope around the AM or sideband signal. So this is not a measure of the transmitter full power. This is what we are driving. And remember, the amplitude of an AM signal or a sideband signal is based upon the actual audio going in. It's a reproduction of the audio, okay? Amateurs who use any frequency in a band are allowed to use any frequency in a band, but you have to be careful when operating near the ends of bands. That's the important part. And I'm going to cover this with you, particularly in FM. In FM, we use FM wide. Commercial industry hasn't been allowed to use FM wide since the 1970s. And it opened up a realm of cheap equipment when commercial companies dumped them. We hams grabbed it, and we got into the repeater game. But because of that, FM wide is actually 15 kilohertz wide. So when you are operating near the edge of either band, and for the most part, most FM signals you're going to be transmitting are going to be VHF and above. Not all, but most. That means you have to stay away from the upper edge of the band. The lower edge of the band is already allocated for other things if you look at the band plan, and you probably won't be down that low in each band. You want to stay at least 7.5 kilohertz away from the edge of the band, because your band is 15 kilohertz wide. That's its deviation. That's how wide the signal will go at maximum when you're talking. It'll go narrower and wider to transmit the data that relates to what your audio is. But at 15 kilohertz, your center frequency is right in the middle of that 15 kilohertz. So you got to remember that you're going 7.5 kilohertz above and 7.5 kilohertz below. And so you want to stay away from the edges by the width of what your signal is, FM being the widest phone signal we use. It's good to keep that in mind. Now, I'm going to jump ahead, the book does, so we're going to do it too. I'm going to talk to you about a device called a dummy load. Everyone should buy one. Not right away, but someday in your life, you want to have a dummy load. A dummy load is nothing more than a 50 ohm resistor. And they don't show one. I forgot. I remember now. It's nothing more than a 50 ohm resistor that is a pure resistive resistor. Resistors come in they come in various physical types, but they're divided into two categories. One is inductive and one is non-inductive. Heavy power resistors are generally inductive resistors. They are resistors. They're made from coils of wire around the insulator, but those wires are highly resistive wire. And for DC applications, they work out fine. But for AC applications, and particularly radio, every inductor does what with the frequency? It changes its X of L, right? And we have a formula for that. So you don't get the same effect, the same load of a inductive resistor off of a transmitter than you would from a pure resistive resistor. Pure resistive resistor has virtually no inductive component. Because of that, to a 50 ohm transmitter, a 50 ohm dummy load, which is a 50 ohm resistor of sufficient wattage to handle the load of the radio and then some, hopefully. You don't want to use too small resistor, you will smoke it. Even a small dummy load on a high powered transmitter or amplifier is not a good plan. But it will act as if you have a perfectly tuned antenna on the end, but it will not radiate. Dummy loads are designed to convert all of the energy into heat. And they are perfect for testing your radios when you want to calibrate or test things or set things up. Now, there's some sorts of things you cannot do with a dummy load. One of them would be you can't tune an antenna, obviously, with a dummy load. You have to put some sort of signal on that antenna, and it has to probably radiate a little bit. You don't have to tune a radio, tune an antenna at full power, but you can do something like tune an amplifier. You can check your power output by going into a dummy load, and it won't go out over the air. You can make adjustments to a radio, and you should always make adjustments into a dummy load. Okay. DSP and SDR radios. SDR stands for software controlled radio. DSP stands for digital signal processing. I'm going to cover those two things real quick for you. DSP, both of them, by the way, both of them involve a microprocessor or a microcontroller. DSP takes an audio signal and takes usually the audio, but takes the signal and digitally it converts it into a digital value. It takes the analog signal and digitizes it. Then it takes that and it processes it through a microcontroller, a microprocessor, and software manipulates the bits. And then it restructures it back into an analog signal with an analog to digital, I'm sorry, a digital to analog converter. So it enters an analog, it enters as analog, which means a waveform, goes into a digital analog to digital converter, which is a chip or a circuit that converts it to on and off bits, processes that through a microprocessor, and then sends it back to it manipulates it, sends it back out to a digital to analog converter and restructures it. When you hear digital sound on your radio, on your audio devices at home, on your phone, this process has been done to them already. It allows the system to control and shape the audio. It can be done it's done commercially nowadays for audio reproduction and to get rid of everything imaginable, like in recordings. But in our radios, it does things like noise reduction, and it filters out various unwanted signals, and it can even be used to notch things out. And it can even do audio equalizing, and audio equalizing is basically reshaping, redefining the audio. It's a pretty handy tool. Some new radios, a lot of the new radios have digital speech processing aboard. There are limits to it. You can't take out too much or you'll start to distort things. Too many bits kind of ruins the pie. SDR stands for software defined radio. Basically, that's what they are. They're radios built from microcontrollers, and the microcontroller actually builds everything, even the waves, even the oscillators, the oscillation, the waveform is built in a microcontroller. It's pulses that are converted and made into an analog signal in the same digital to analog process. And it allows for some really, really cool radios, because we are now using far more stable microcontrollers than simple tune circuits of the past. So today, most radios are at least somewhere in between. So they have at least some microprocessor control, some processing. We also have other forms of filtering. We have analog filtering, and they all work pretty close to the same way. They all have the same limitations. Their qualities are a little different. Some people prefer old analog filtering, and some people prefer the new digital DSP processing. And some DSP processors are better than others. Some software control radios are superb. Some are not. It's just, I guess it's a matter of what you pay for. I already told you that overmodulating a FM signal or causing a FM audio to be driven too hard will cause you to over deviate. And excess deviation is over deviating. And I've told you why. It's just as simple as that. It's not much to cover. I already covered the AM, how the AM signal and over deviation, why that causes, or over driving. I mean, there's no deviation, but it's over modulation, and why that holds true. Are there any questions about that, all of this? All right, we're going to go quickly through receivers. Receivers are obviously there to pick up what's out there, and they're picking up very, very weak signals. And inside a receiver, we end up with some fantastic stuff. And I already covered what a AF gain is, which is a volume control thing, and I'm not going to go through that, but I want to talk about something called, a lot of receivers have something called automatic gain. Automatic gain control, AGC, is a feature which, well, let me give you the easiest way to understand how it works. Receivers use AGCs, and so do transmitters. And what an automatic gain control circuit does is easy to understand if we talk about TV commercials. If you're ever watching a TV show or you're watching a movie and all of a sudden the commercial comes on and it comes out blaring, and you sit there and go, why can't they make it so it doesn't blare at me on the commercials? Well, the answer is because for a few dollars more, they could add an automatic gain control circuit, and it could do that. Automatic gain controls try to keep the level of the audio, whether it's in a receiver going out or a microphone going into a radio. They try to keep them at a level constant. It's very handy if it works right. When you got one guy whose signal's really strong and one guy who's weaker, you don't have to keep turning your volume up and down, because the one guy you can barely hear, and the next guy, when you have it loud for the other one, it just blares. Squelch circuits. I'm going to cover this really easy. A squelch circuit is a circuit that turns off the audio until a certain level of signal enters the receiver. When that signal is sufficient enough, depending on how you've adjusted the squelch, it will, quote, break the squelch. The squelch will open, audio will go to the speaker. When that signal drops off, the squelch will resume and it goes to quiet. That's all there is to it. Oh. There are two key factors of importance when we're talking about any receiver. By the way, these questions, we get to the question parts during the question and answer. Two of the most important features of a receiver are sensitivity and selectivity. And we're going to cover those. Sensitivity is the minimum detectable signal level, and we usually measure that in microvolts, that a receiver can hear. It's what the weakest signal your radio can pull in. Most ham radio receivers have incredible sensitivity. I can tell you cheap Baofengs do not, but they work. Don't knock them. Okay? So sensitivity is the ability, or defined as what the lowest or minimum detectable signal level is. Obviously, you want the most sensitive receiver you can get your hands on, but there, of course, are limitations. I'm going to skip preamps up there for a minute and get back to it. Selectivity on a receiver is how well it can discriminate or separate between different signals to literally, in a way, exclude one when you're tuning the other. And selectivity is really how well that radio can pick out the frequency you really want. So in selecting receivers, when you're looking at receivers, you're looking for maximum selectivity and the smallest sensitivity. Now, a preamp is a device that comes between an antenna and a receiver, and it amplifies the signal going into the receiver. it can improve the sensitivity and the selectivity of a receiver to have a preamp on the other end. But there's a trade-off. When you put a preamp in, you're amplifying everything, not just what you want to hear, but all the garbage you don't want to hear too. So not only will it bring in your signal stronger and easier and make it easier for the radio to discriminate, but it will also introduce more noise. So that limits the maximum amount of amplification we can put on most preamps. Although today there are electronic preamps out there that are phenomenal, and they really can offer a great deal of amplification, taking in some of the tiniest little signals and making them strong enough for even a medium quality receiver to handle. Okay. And so when we bring in that noise, next trick is we got to get rid of it. I already covered how we did it digitally, but we use filters, whether they're digital or analog, to filter out what we don't want. And there are several types of filters. One is the bandwidth filter. A bandwidth filter narrows how wide the receiver will hear. It narrows the band. A narrow bandwidth filter is very, very small in value. So if you have a single sideband narrow bandwidth filter at around 2.4 kilohertz, that's pretty narrow because a single sideband signal is usually around 2.8 kilohertz. You're going in real tight. When you use such a filter, you've got to tune very precisely at dead center because you're narrower than the whole signal. And you're already going to get a little bit of distortion from it because it's going to be clipped off somewhere. If you're not dead centered, it might not be intelligible. But it can eliminate noise on either side, above or below the signal. So I'm going to kind of jump ahead so we can cover this. There are two other types of filters, and we're going to get it comes up, but I want to do it here. The two other types of filters are high pass and low pass filters. High pass filters allow everything above a certain frequency to pass through. So if your high pass filter is set at 100 hertz, or let's go 100 kilohertz, everything above 100 kilohertz will go through to the receiver. Everything below 100 kilohertz will not go anywhere but to ground. There are low pass filters. Low pass filters will allow anything below a frequency to go through, but nothing above it. A low pass filter gets rid of, say, everything below 100 kilohertz if it's tuned to 100 kilohertz. Everything above 100 kilohertz will go to ground. To understand the difference between low pass and high pass isn't hard. To understand the difference between high pass, low pass, and bandwidth doesn't wipe out everything higher or lower. Bandwidth only lets through a certain narrow area of frequency. So a bandwidth filter just takes a width of the band and says wherever you're tuned, this is all you're going to hear. High pass or low pass filters say, regardless of where you're tuned, anything above this or for a high pass, that'll come through and everything below won't. And for a low pass, it's completely the opposite. Everything below this frequency you could hear, but no matter where you tune, anything above it is not going to be hearable. Why do you use high pass and low pass filters? Well, if you're transmitting HF signals and they're getting into somebody's FM radio, well, the FM radio doesn't need any of the frequencies down low where an HF frequency would be. So if you put a high pass filter on it, all the lower signals would not pass through. It wouldn't get there, and the interference will go away. And the same is the other way around. If you're trying to operate on 144 megahertz and you're hearing some motor noise, which fundamentally is a 60 hertz signal, well, a high pass filter is what you want to get the high signal in. A low pass signal is not what you want, right? So that protects you. But if you're transmitting on 440 megahertz and it's getting into your wife's baby monitor, and that baby monitor, or even some TV channels, but let's go with something simple. That baby monitor is down at 50 megahertz. Why, then you don't want the high frequencies to get into that baby monitor. So if you put a low pass filter on it set for, say, 60 megahertz to pass everything below 60, that baby monitor will be fine. I'm not saying that baby monitors are on those frequencies, but I'm just giving you an example if it were. Okay. RIT, receiver tuning. I already covered that. I told you that's the control that lets you adjust to, so that if somebody's off frequency, you can tune them in without changing your radio's fundamental VFO or variable frequency tuning knob. Sometimes RITs are called RIT, are called clarifiers, and they're labeled as clarifiers. Whether it's an IRT, a RIT control, or a clarifier, they're the same thing. And their purpose is to change the frequency of the signal to compensate for somebody who's slightly off. There's a filter on many radios called a noise blanker. It's particularly sharp for, or good for getting rid of sharp, like pulses and arcs type noises. Really handy for automobile ignition system noise and things like that. A noise blinker is usually an on-off device. It's not adjustable, but when you turn it on, it will try to take out those pulses. All right. Now, your receivers will likely have a meter on them called an S meter or signal strength meter. Signal strength meters display in S units, okay? S units, this is a little difficult to swallow. S units go from S1 to S9. Anything, the first increment greater than S9, we measure those in dBs. So it'll go to S9, and then it will say 10 dB over an S9, 20 dB over an S9, and so on. An S signal is actually 6 dB for every one of them. And we go from S1 to S9, we're going 6, 6, 6 dB. And remember, every 3 dB is doubling. So S meter units are major moves. They're quadrupling the strength for every signal all the way to S9. So it just happens to be the way we've taken a convention for measuring it. There is some reason for it, but it's far more involved and really not worth explaining. Okay. Because it really doesn't change the fact. It's just easier to just deal with the fact that we measure in S1 to S9, and then above that it's in dB divisions, because after that point, those huge jumps that S units represented, they'd be way too great a range for most radios to handle. Okay, so I've covered what a squelch is. I've covered if you read the rest, it gives you a little detailed text about tightening a squelch. That all makes sense. The one filter I want to talk about is called a notch filter. A notch filter is sort of a backwards bandpass filter. A notch filter, though, is much narrower, and it picks a point that you want to notch out. You can usually tune them. They can be sometimes widened a little or not. Purpose is, if you have some noise on one little pecky spot, a notch filter will let you notch out that little spot. So instead of selecting a spot or a portion of the band that you're going to listen to, it picks one little spot in the band that you're not ever going to hear, or hopefully not hear. And so all of those are a part of your noise reduction system for radios. But modern radios with digital controls and processors have one more tool. And they actually have a noise reduction circuit, software that actually removes noise during the digital processing. So all these are controls on radios. Not every radio have them all, but they're all out there. And sometimes you need them, sometimes you don't. You won't find them on handhelds or anything simple, but more advanced radios you will. One thing I really, really want to bring up is that when you're dealing with handhelds, a lot of guys have the attitude that, well, if I get a handheld and amplifier, I've got the same thing as a mobile. Handhelds don't have the receiver qualities and the sensitivity or selectivity of a full-size radio. They were never intended to. So you're going to be sacrificing that. They also don't have the transmitting circuits and quality and filters as a full-size transmitter. When you amplify a 5-watt mobile, I'm sorry, a 5-watt handheld, and you amplify it 10-to-1 to get a 50-watt audio into a mobile antenna, it'll work. But you're also going to be amplifying a lot of noise. And you have to be careful of that because it does become a problem. You can get out of compliance real easily that way. I want to talk about transverters, though, and transverters are a special type of mixing equipment. Transverters take a frequency and they mix in oscillator frequency, and they output a new frequency, just like any other mixer circuit I described earlier. But their function is more of a system, and it's designed so that a transverter allows you to take a radio that works on one band and it transverts. It doesn't just change one frequency, it changes the entire range of frequencies of that radio. It uses mixing techniques just like the simple mixer, but it allows you to, for example, take a 10-meter radio and put it on, say, 1.2 gigahertz or 220 megahertz or any frequency you want to transvert to, up or down. I also want to bring up a cousin of the transverter, okay? And that's the receiving converter. A receiving converter the transverter handles the transmission. Receiving converter handles the reception. A receiving converter will, for example, allow you for example, you could put a receiving converter on your car mobile radio or your car radio in the car, in between the antenna and the receiver, and you would be able to listen to, say, one of the ham radio bands on your car radio. That's what a receiving converter does. Transverter converts transmissions. Receiving converter converts receiving. With that, I'm going to talk about a cousin of both of them for a second. Aboard satellites, we have something called a, oh, what is it called? Oh gosh. Oh, I gotta remember at the top of my mind. It'll come to me, guys. Remind me later. I'll look it up. But when we talk through a repeater, we send the signal out, goes in a receiver, uh, and it comes back out to us from a transmitter at the receiver site on a different frequency. When we transmit, though, through some satellites, they do it with a, oh God, it'll come to me, guys. But anyways, they do a different technique. They do a technique which is very much like a transverter and very much like a receive converter. They actually take in, but they take in a whole block of spectrum and they move where that whole spectrum is transmitted back out to another portion of spectrum, usually on a different band. That way you can listen on one band and transmit another, and multiple people can use the satellite. I think that maybe still is called a transverter, a transducer, maybe. Anyway, and so those are all related technologies. Circuitry wise, they work very similarly. I want to cover the basics of what digital means at the rudimentary level. In every microprocessor, every computer circuit, every system, the root of it is uh, basically a number of switches. In this drawing, I've laid out 1, 2, 3, 4, 5, 6, 7, 8 switches. If we design the first switch as being 0 or 1, if that switch is on, this is the best way I can illustrate it, then that value is 1. If that switch is off, in fact, I can probably do this a lot better. I guess not. It's not going to let me cooperate with that. Okay. If that's off, that value is 0. All these values are 0, okay, unless they're turned on. If the second one's turned on, then we basically make that value 2. If both this one and the first one is on, it's 2 plus the one before, which is 3. The next one over is 4. It doesn't want to move. It locked up again, guys. Sorry. I don't want to take time to reboot the computer, so I'll just, there we go. Is it going to move? No, it's not going to move. Okay. But the next one over is 4. The next one over is 8, and so on. When we talk about digitizing, we use a digital circuit to take the audio and basically, based on what its waveform is, we convert different points into values and store them by basically turning on switches in what we call memory. Memory circuits are a bunch of solid state transistors that we either switch on or off, and depending upon where they're located, they represent a number. So if we had the 16 and a 2 on, that would represent the number 18. Now, depending on what we apply this to, we can make that represent a numerical value for mathematics. We can represent characters like text, like what you see on the written page, because we use what we call ASCII. ASCII as American Standard ASC, American Standard Code number 2. II is the ASCII end. And we ASCII is a process of we've converted all of the letters and characters on a printed screen to have a defined number to represent them. So the other thing is we can, when we have them represent values or numbers themselves, they can represent things like the signal height of a wave, the width of a wave, and all the information that pertains to the wave that we started with when it's in radio. So it's as simple as this, but it gets a little hairier when you get to the fine details. Fortunately for this class, you don't need to know the fine details. Okay, I'm going to stop the share and we're going to go back to the book. It'll become obvious later on why I took the time to explain that. So when I tell you that we're digitizing a signal, we digitize the signal by splitting it up with a computer, a microprocessor, and storing the values that describe what that signal is. Now, we talked about how it was done for audio, but in digital communications, I talked about quickly how we can digitize and then we can basically pull some of those bits out and change the shape of an audio. For digital communications, though, we want to accurately reproduce what we're doing. So we want to sample everything and then we want to send it out digitally and reproduce it accurately. The earliest form of digital communications is CW, Morse code. It is a digital communication because it's on and off, but we use a timing, long and short, instead of a digital switching circuit. We can't transmit digital switching circuits. So we have to have some way of sending that information anyway. And the way we do it is by reproducing either audio that fluctuates on and off with timing so that we can decide how long determines when the next bit is and the next little box that gets checked, so to speak. Or we do it with audio that's multiple tones going back and forth to be on and off. Imagine this: if you have a certain period of time, you're going to send one byte of code, one character, one strip, like I just showed you, and each is 1/10 of a second. Well, the first 1/10 of a second, if you've got an audio on tone, that character, that box is on. The next fraction of a second, if it's the second tone, which is off, that bit is off. And when we get all done, we fill in all the boxes. Then the computer on the other end of at the receiver has that letter, that character, or that instruction, whatever it might be. Problem with this is, as you can now imagine, it's prone to, you could make a lot of mistakes doing that unless you have some way to check to see if you didn't make a mistake. And we do. We have methods for counting up the the bits and sending a number that says this is what you should have, basically, and then methods of verifying it and so on. All that complexity is something called protocol. Communications protocol, digital protocol, is defining how we're going to package the data up, send it over the air, how we're going to verify that the ones and zeros are correct, and then exchange the information accurately. Sometimes we include systems that whenever there's an error, protocol will give instructions to resend in order to correct things. Sometimes we have protocols that actually send back what we sent and compare it in the first computer. And then the first computer will tell it, nope, you need to fix this one, or so on. So, uh, so we began with teletype as the earliest digital means of communications. Teletype, radio teletype did not have good error checking. So you had to be precisely on frequency. It had to be all set up perfectly. But it worked. You sent a digital signal, and when you typed on a teletype key machine, it created the sounds that were going, or the pulses that were going to the transmitter. The transmitter reproduced those pulses, sent them over the air. The receiver at the other end received those pulses, and then the keyboard at the display device, which was a printer, printed out exactly what was sent. Eventually, we started using computers to do this, and we got more complex digital modes for texting and things. We started with things like packet radio and more complex than error checking forms of teletype, and they evolved. Today we have dozens. We have uh, probably the most popular right now you're going to run into are FT8 and WSPR. Details of which I'll tell you to read up on, guys, because there's way too much cover there. But everything from your Wi-Fi at home, your text messaging on your cell phone, they're all based upon the same concepts of protocol, and they're varying protocols, but they're all based on the same techniques. Now, to go along with this, we are nowadays also using digital phone or voice communications. We don't actually digitize your voice and send the digital, not in the purest sense. We actually send your voice in, and well, it depends on the radio, but usually the receiver actually, or the transmitter actually takes in your voice, your audio, and then we digitize the signal that's going out over the air because it's still FM modulated. But we digitize it and we send a digitized version of your voice, and the radio at the other end reconstructs it. Again, different protocols exist, and there are different systems out there. There's a system called D-Star, there's C4FM Fusion, there's DMR radio, and P25. There are others. There are many others. Unfortunately, they're not all directly compatible. They're not at all compatible with each other 100%. Although there are interfaces available, boxes that can let you receive one and transmit the other type of thing. But usually you have to have the same radios on each end. The advantage of digital radio is, well, first, it can be compressed and you can send it in smaller bandwidths. Second, some of them, like C4 FM, reproduce audio phenomenally. DMR radio is probably the least quality of reproduction, but it has the advantage that it more efficiently uses power in a narrower bandwidth, so it gives you a greater range. So you're going to find a great deal of digital coming up in the future. And audio, digital, and we're even beginning in the amateur world to use digitized TV. You already have digital TV if you ever Skype, and you're using digital TV right now in this class. This is how this whole trick is done. It's all the same technology, just different protocols. Okay. Your book covers where you'll find packet on the UHF and VHF frequencies. It covers frequency shift keying, which is another digital mode, and it works the way it sounds. The frequency or shifting the frequency high or low produces an on or off. A timing interval of how long between each on and off determines which bit is being sent in a package of bits. And the protocol for that is determined by the software and the controlling device, the device that interfaces to the receiver and transmitters, sort of interface the computer to the transceiver. Those devices are nodes. Nodes are a spot where information is being handled. And we refer to them as terminal node controllers because the terminal is endpoint. A node is where information is passing, and the controller is controlling how the passing is being handled. Okay? So, you're going to find that interfaces and terminal node controllers are available for just about every type of digital communications, and including voice or phone communications. This right here, hope you can see it. Somebody shake their head, wave a hand or something. But this right here, I think you guys see it in my little window. And this right here are called digital hotspots. They allow me to link to the internet and take my signal from like a handheld radio, link to the internet, and connect it to a repeater many miles away via the internet. Hotspots are a form of well, they're not a repeater. They're a form of digital conversion device that interfaces one type of signal with another. Programmable hotspots like that can be actually set up for any mode, and they will allow you, for example, to interface to a mode that you may not have. Okay. Now, getting back to digital messages, I already covered that there's checksums. There's also in the protocols in the standard of most protocols, a header, which is information being sent at the beginning of the data, just before the data, and a checksum usually at the end. The header is there to get the receiver ready for what's coming. The checksum at the end is for verifying what the signal is. There's often error checking detection involved that can send automatic requests to retransmit. They refer to as automatic repeat requests. And it all of these combine to allow for some really accurate data. It's seamless. You don't see it, you don't notice it, you don't have to interfere. Some really bright guys wrote this stuff years ago. Okay. Read up on them. I'm not going to go through every single type, but they're pretty much the same. The different modes of digital. And you'll find that some of one or two or three or maybe all of them will be appealing to you. Um, Today in the modern system, I want you to be aware and you should know of something called automatic packet reporting. Automatic packet reporting has become really popular because it means that your transceiver, your radio, can actually have the ability to link with global positioning systems. And when it transmits, identify where you are. Systems that have this, like the uh, Yaesu FTM radios and some of the ICOM radios, they allow you to know when you're talking to whoever you're talking to, where they are, exactly how far your signal's going, how far apart you are, and they really add a new dimension to the radio world. Okay. And it's particularly handy for mobiles. And so that allows you the ability to track where your contacts are going. FT8 is another system that's also built around this concept, but FT8 generally does it manually. You enter where your location is when you set up FT8. Automatic APRS, automatic positioning reporting system, automatically, even when you move, when you travel, recalculates where you're at and keeps it itself updated. It's a big difference. Okay. Now, hooking up the digital station. Well, it's going to involve usually a computer, especially for something like digital voice. It's going to all be built into the radio. For something like texting via packet or FT8, you're going to have an interface. It will either be an TNC uh, or an MPC, which TNC stands for Terminal Node Controller, and MPC stands for Multiple Protocol Controller. I already told you what protocol is. So multiple protocol means it can handle various protocols. TNC means that it is a terminal node controller, usually one protocol. And generally, the way they're going to hook up is they have to take audio from the receiver of the radio, and they have to take audio from the computer and output it into the transmitter to be transmitted. So in order to do that, they also have to control the push to talk. So there are three basic connections all these interfaces will require. They'll require a connection to push to talk, a connection to audio in to the radio, a connection to audio out from the radio, and then they will require some connection to the audio in of the computer and the audio out of the computer, and a third or fourth or fifth, I've lost count, guys, I'm sorry, but a final control that might be involved will be an actual digital control from some radios directly between the computer and the radio, or directly between the computer and the interface or node controller via USB or serial. serial is not used as much today as it once was because we use USB, which is a newer form of serial communications. If you want to know the difference between the old serial interface and modern USB, it's a little side note, but the difference is that fancy word protocol. They just changed how things got handled. Um, Talk about something that you don't see, but it's there. Digital systems have something called gateways, and gateways allow you to get from one system into the other. This is why a device like this can work, a little hotspot. And it's also, most gateways will allow you to have forward and storaging of messages so that if somebody's not there right when you send it, it can be picked up later. There's a lot of tools in the digital world. You're familiar with them because you know how they work from text messaging. But this really all came, in this case, from amateur radio. We were doing this 40 years ago. Back then, it was pretty revolutionary. Read through the book. It tells you, confirms what I'm saying. But I want to jump to batteries and power supplies because we need to get through it. Power supplies. There are two basic types of power supplies. One is conventional analog power supplies. It has a huge transformer that converts AC to a lower voltage. And then it has a rectifying circuit that converts the AC to DC. It has a filter circuit that filters out any AC waveform. And last, it has a regulator circuit that regulates the output. Analog power supplies are simple, but they're heavy because of large transformers. The larger you need them, the bigger, the bulkier they are. They have advantages. One of the advantages is they tend to be much cleaner than digital power supplies. Digital power supplies take an AC signal and a switching circuit controlled by a very small analog power supply, turns on and off a switch type of transistor or a series of them, and they just take off little bits and pieces of the power coming from AC. In other words, they turn on when the voltage is at a certain voltage and turn off when it gets too high, and another transistor will take the negative side and turn it on and off. The negative side of the wave, turn on and off on that. And if one is an NPN resistor and one is a PNP transistor, well, then the NPN will turn on and off on the negative side. The PNP will turn on and off on the positive side. And you will get pulsating DC coming in because they will both end up making, if they're wired properly, a portion of the wave as solid pulsating DC. Filter circuits on the digital power supply then smooth that pulsating signal out. Reason digital power supplies can make noise is because they sample by switching on and off. And by switching on and off very rapidly, they're an oscillator. They create harmonics. They create RF noise. The better the quality of a digital power supply, the better filtration. Some of them today are so good, I wouldn't hesitate to use them, but there are a lot of terrible ones out there. Small electronic devices with small little AC adapters today that don't hardly weigh a thing are digital power supplies. And many of them are not very well filtered. You're going to find out in the radio world, they make a lot of radio noise. And you're going to get interference from wall warts like crazy. Those are digital power supplies. So the advantage of a digital power supply, though, is that it doesn't have a great big huge giant transformer anywhere in it. They're much lighter in weight. They're usually smaller, more compact, and easier to carry around or move around. It's a 6.5 and a dozen of the other, one or the other, as to which one's a better choice. I tend to favor analog power supplies until I have to move them. So, when you're picking a power supply, remember the power formula we learned? P equals IE. Well, you need to know how much power a power supply is going to demand, or your radio is going to demand of a power supply. A load draws what it is going to draw from the source. So whether it's a battery or a power supply, you've got to have enough current capacity and voltage for the load. Now, your radio is going to work at 13.8 volts, 12 to 13.8 volts roughly. So the power supply has to have enough ampacity so you can put out the wattage that it needs. The power formula is P equals IE. So the voltage times the watt times the current, P or E times I, have to be greater than the power that the transmitter is going to consume. If you've got a 100-watt transmitter and it's at 13.8 volts, if you divide 13.8 into 100, you're going to get somewhere around 7.5 amps. But transmitters are not rated by the power they draw in. They're rated on the power they output or put out. Most all ham radio final amplifiers are Class C amplifiers. Class C amplifiers are only, I think it's Class C or Class C. I gotta look that up. I get them mixed up sometimes. They're only 50% efficient. So if you're transmitting 100 watts, it needs 200 watts to make that power. So now when you divide 200 watts by 13.8, you get closer to 15 amps, 14 point something or 15 point something. Somebody can do that math, it won't matter. So the point I'm trying to make is when you want to calculate what size power supply you need for your radio, take its power output, multiply it by 2, and divide that power times 2 by 13.8, and that will tell you the minimum power you need to run that radio. Two things that go along with that. First of all, buy a power supply that's bigger for 2 reasons. One, this is important. You're going to have other devices you're eventually going to want to hook up. You need spare power if you add another radio, a light, any 12-volt device that you hook up to it. 2, when you buy a power supply, it is rated for intermittent use. So if it's rated for 20 amps, it's not full 20 amps continuous, but intermittent. And so you really got to kind of derate that down. So if you want to draw 15 amps out of a 20 amp power supply, it sounds like it should be plenty. It's really not. You should probably be around 22 amps because of the fact that intermittent means that there has to be a certain percentage of cooling time. It's got to run for a while, cool for a while, run for a while, cool for a while. Uh, and so if you're operating like single sideband, or if you're operating AM, well, when you transmit, your voice makes more power, less power go out because it's amplitude based. And amplitude modulations means that you will be fluctuating. You might get by real well with a 20 amp power supply, but if you're running FM or some of the digital modes or super high speed CW, why then you might just destroy a power supply because it won't have enough uh, power dissipation ability. You will be pulling too much power through it at a time for it to be able to keep itself cool. So keep those things all in mind. A power supply, as I've told you, they the most important feature is its current carrying capacity. The second most important feature is just probably equally as important is exactly how well regulated it is. A crude simple power supply has a voltage at zero load, and without a regulatory circuit, whenever a load took to it, the heavier drain the load is, the higher the current load, the more it will drop in voltage. A regulated power supply will keep that constant throughout its designed range. And so a 13.8 volt power supply should remain 13.8 volts across the range you would use it. Wire size. Here we go again. Another thing, remember the E equals IR uh, formula, the ear formula. When you're deciding what kind of wire to run between your radio and the power supply or battery of a car, you have to consider that there will be in the wire a voltage drop because you're working at low voltage. 12 volts is very low. There's voltage drop in every wire. If you're running a 100-volt circuit in your house and there's a 1-volt drop, it's not significant. But if you're running a 13.8-volt radio and there's a 1-volt drop, that's very significant because you will have lost almost a tenth of your power running to that radio. And subsequently, that will force more current to flow through the wire because of the resistance of the wire. So to compensate for this, you want to get as big a wire as possible to feed your device. Calculate by using the current formula. You know how much power the radio draws. You know how much you can calculate how much current because it runs at 13.8 volts. And again, you do the same thing we did earlier. You multiply the 13.8 volts. I'm sorry. Yeah. Let me start over. You divide the 13.8 volts into the double of the power. You will get the current that radio runs on. Okay. Now that you know the current the radio will run on, this is the simplest way to do it, but you can look up your formulas and you can use the square formulas for calculating this too. It's in your book. You can do it directly, in other words. But anyways, once you know the current, take that current, multiply it times the resistance of the wire. You can look that up. They actually have charts that tell you if you have this much wire, this is the resistance. By multiplying the current you're going to run through it times the resistance, you're going to know what the voltage drop of that wire is for that length of wire. The voltage drop of that length of wire, you want to keep it reasonably low. If that wire size isn't going to do it, go to the next size bigger or keep going bigger till you get what works reasonably. Generally speaking, that's going to mean for most radios, usually a for 50-watt radios, I would use the number 12 wire as my minimum. For 100-watt radios, I would use a minimum of number 10. And you might find for a little bit longer runs, you have to go bigger for both of those. So I might go a number 10 for a 50-watt radio and a number 8 for a 100-watt radio. And the book talks about making connections and hooking up and so on. When you're hooking up in an automobile, hook up to the battery, put a fuse in between the battery to the positive wire of the radio, hook the other side to wherever the battery itself, whatever point the battery itself bonds to the chassis. Now, it doesn't physically have to be at that point. Usually the closest spot is the negative terminal of the battery. You will have a lot fewer problems if you do that. Do not rely on the chassis of the body of a vehicle as your ground return path for your electrical connections. Batteries are made of cells. Every battery means it has a group of cells. Every cell is 1.5 volts, 1.3 to 1.5 volts, maybe 1.2 and a half to 1.5 volts, depending on the design, the type of the battery, the chemistry. There's a chart down there on batteries and everything. It's self-explanatory. I don't think you need my explanation, but batteries are rated in amp hours. And an amp hour is how many amps that battery can deliver over the course of an hour. Now, honestly, not every battery can physically deliver the amp hour rating for an hour. It may have to, some types of batteries have to be discharged way slower than that. But that's as much as you can get out energy-wise. So a 100 amp hour battery, in theory, should have enough power to give the equivalent of 1 hour at 100 amps. So 10 hours at 10 amps might be the equivalent. So if you want to know how long your system will run on a given battery, you're going to be shocked at how short it is for many transmitters. But that's how you calculate it. Whatever its amp hours rating is, that's how long per hour, however amps you're running it on. And you divide that into its amp hour rating, you're going to get how long you can run it. Or I think I said that right. So going back, if you have 100 amp hour battery, and which is quite a big battery, mind you, and you want to run a 50-watt radio, that 50-watt radio is 100 watts of input power divided by 13.8 volts. That's going to be somewhere, I believe, around 3.5 amps. So you take 3.5 or 4 amps, you divide it into 100, you're going to get 25 hours. Will it be exactly 25 hours? No, it will not. Because not all battery chemistries can allow you to draw 100% of its amp hour rating out of it. Some batteries, of course, like primary batteries, which are not rechargeable, they're designed to run till they go dead. Some rechargeable batteries, though, like lead acid batteries, are only designed to go down about 30% before you do them damage. Lithium batteries can go down to about 90%. But a lithium battery that goes to 91% becomes what they call an exothermic anomaly, a violent exothermic anomaly, meaning it bursts into flames and you can't put that fire out. So lithium batteries have a protection circuit called a battery management system added in. Never run a lithium battery without one. Don't hack lithium batteries. Lithium batteries generally, except real tiny button ones, have battery protection or battery management systems. And there's a circuit board that monitors the battery during charge and discharge, cuts off the charge when it gets to a certain point, cuts off the discharge when it gets to a certain point. If you exceed that value, there's a short window you can get away with it, but it's risky. If you do, more times than not, you cannot get that lithium battery to charge again because the battery management system doesn't have enough power to engage itself. If you go beyond that point, you will start a fire or an explosion. Don't mess with playing with the range of lithium batteries.